And hi, how are you doing? My name is Lonnie. We're back here again, and we're going to continue with a previous subject matter that we've spoken about, and that would include solution concentration in terms of chemistry. Note that we had previously spoken about percent by mass, percent by volume. Today we're going to speak of 4 of the ways in which solution concentration can be expressed. And those particular methods would include molarity, dilution equation, molality, and last of all, we'll finish up with mole fraction. So, having said that, let's go ahead and get started. First of all, let's identify molarity. Molarity, note that it can be expressed as a uppercase M, and it is, in fact, is equal to the number of moles of solute per liter solution. Okay, so the number of moles per solute per liter solution. Note that moles, let me scroll that up a little, and let's just as a reminder, note that recall that moles, and remember mole, in fact, is expressed by a lowercase n, is equal to mass in terms of grams divided by the molar mass of the substance in question. So hence we have that, we're ready to go ahead and calculate and solve a problem, if you will, in molarity. So having said that, let's go, here's our first problem, and in fact, let us blow that up. Here it is. First problem reads as such. A 100.5 milliliter IV solution contains 5.10 grams of glucose. What is the molarity of this solution? Let's first of all, let's go back to the smart board here. And one of the first things that we want to identify, first of all, and let me rewrite the equation in terms of how molarity is expressed conventionally. Again, I'm going to just abbreviate, utilize the symbol M for molarity. Molarity equals, again, moles of solute divided by liters solution, SOL area for solution. Okay, note that in that problem, we were in fact, the unknown is, we want to calculate, I'm going to put UNK for our unknown, and we want to calculate the molarity of the glucose solution. Okay, that's what our unknown is. Let me scroll that up a little more, give us some room. Now I'm going to identify, that was the unknown, I'm going to identify the given information that was provided for us. First bit of information was given that the volume solution was equal to 100.5 milliliters. Now note, I'm going to go ahead and convert this to liters because in the expression of molarity, solution or volume solution, and in fact, is expressed in liters. So let's just go ahead and convert this, move this decimal point over 3 places to the left, and so hence that equals 0.1005 liter. All right, the other piece of information that they provided us was in fact 5.10 grams of glucose. Of course, this is our solute. Now, recall that moles, in fact, is the relationship between mass in grams divided by its molar mass. So the molar mass we have to calculate, let's write this directly below that. The molar mass of glucose, in fact, is approximately 180.16 grams per mole. Okay, it looks like we're ready. We've identified the unknown, we've identified the given, and we're ready to plug in our data in terms of our expression of molarity. So let's go ahead and rewrite this. Molarity, in fact, equals moles of solute divided by liter solution. Okay, let me scroll that up a little more. Okay, let's identify the moles of solute. That was, in fact, the moles of glucose, which was our solute. We were given 5.10 grams, again, this is of glucose, our solute. Molar mass of glucose, in fact, is approximately 180.16 grams per mole. And all of that is divided by the liter solution, which in fact we calculated from milliliters to liters, which in fact was 0.1005 liter solution. Okay, we'll continue on. Let me scroll that up. And so hence, as we plug this data into our calculator, we should get a molarity of 0.282 molar solution, or a molarity of 0.282. to awake too. Pretty fundamental problem if you take a look at it, simple algebra. Well, let's continue on. Let's go ahead and let's do a second problem. Let's go and let's do a second problem here. And we would do our second problem. Let's adjust this for our audience. All right, no, here's our second molarity problem. How much calcium hydroxide in grams is needed to produce 1.5 liter of a 0.25 molarity solution? Okay, well, let's go ahead and let's get back to our smart board. Of course, we know they're pretty smart, huh? Okay, let's get back. Here we go. All right, let's get back to our smart board. All right, this is our second problem. In molarity, again, molarity is an expression of the moles of solute per, or with respect to the solution. All right, first of all, let's identify our unknown. What are we looking for in a problem? Well, the problem, in fact, tells us that we are looking for the calcium hydroxide in grams. So our unknown is the calcium hydroxide, and we want to identify that in grams. This is what we're looking for, calcium hydroxide in grams. Now, that's the unknown. Well, how about the data that they've provided for us in terms of given? Let's identify that. This is our given information. The given information, in fact, was our liter solution. Liter solution was, in fact, 1.5 liters. So we know this is already in the unit that is necessary for calculating molarity. Let's extend that just a little more. So we were given a liter solution. In addition, we were given a molarity of the solution, which in fact, big M, or molarity, was equal to 0.25 molar solution. Okay, now note, we were going to find the grams of calcium hydroxide. So in fact, we need to identify what our molar mass of calcium hydroxide. I'll move this. Let me scroll this down. Calcium hydroxide, and in fact our molar mass for calcium hydroxide is equal to approximately 74 grams per mole. Okay? We've expressed and identified our unknown. We've also done our given. So let's now plug it into our molarity equation, which again is molarity is equal to mole solute divided by liter solution. Okay? Now note that we're looking for grams of the calcium hydroxide, which happens to be incorporated in the moles. Remember, moles are mass divided by molar mass. Let me write it here again. Moles is equal to mass grams divided by its molar mass in terms of the substance. In this case, the solute, in fact, happens to be calcium hydroxide. So let's plug in the data, or first of all, why don't we rearrange this equation, okay? So here's what we have. We're going to rewrite the molarity expression, which is molarity equals mass, again, this is in grams, divided by the molar mass of the calcium hydroxide, divided by a liter solution. And we are looking for this mass right here, the calcium hydroxide. So given this expression, let's rearrange it such that mass is expressed in terms of molarity, molar mass, and also liter solution. So let's go ahead and let's rewrite this. And so hence we have got mass is equal to molarity times liter solution times the molar mass. Molar mass. Again, that molar mass, of course, we're talking about calcium, all right, here to the side, calcium hydroxide. And we are looking for the molar mass, again, let me identify here. We're looking for the calcium hydroxide in grams. This is my unknown. Well, we can go ahead and plug in our data of the given information that was provided. This is, let's continue, our molarity, in fact, was 0.25 molar solution. In terms of the liter solution, we were given 1.5 liters, so times 1.5 liter, and we calculated our molar mass for the calcium hydroxide, which in fact is 74 grams per mole. Hence, we've got everything identified for our expression to calculate mass, and so hence mass, in fact, will come to approximately 27, after our calculations, putting our numbers into the calculator. Our calculation, in fact, is 27.75 grams of calcium hydroxide. Calcium hydroxide, and hence our solution for that second molarity problem. Okay, well, that was the first item of solution concentration, how we can express solution concentration. Let's go to the second one, which in fact happens to be dilution equation. Dilution, so an item, in fact, dilution equation, let's identify this. Let's go back to our smart board. And now let's identify dilution equation, okay? Dilution equation. Now note that the product of molarity times volume in fact of a stock solution, let's identify that as M1V1, and this in fact is my stock solution. And note that stock solution can also be identified as the concentrated solution. And note that we in fact can use this equation to do a dilution of that concentrated, of which it is equal to our new conditions, new molarity, molarity 2, times volume 2, and that would be of the dilute solution. Now note on this. What changes here? Do the moles of solute, do they change? Absolutely not. They don't change. So originally, the moles are the same in terms of my initial conditions, concentrated solution, and my new conditions now, the dilute solution that we're looking for, whether it be molarity or volume. Let's go ahead and proceed. Here's our first problem. So having said that, let's take a look at our first problem for dilution equation. In fact, let's move this. All right, here's our first problem. First problem, in fact, is what volume in milliliters of 2.00 molar solution of calcium chloride stock solution, concentrated, would you use to make a 0.50 liter of a 0.300 molar calcium chloride solution? Hence, that in fact is going to be the dilute solution. So let's get back to our smart board. Let's get back to our smart board here, and then we'll identify what we have. So here we are. We're going to switch colors of pens, give us a little variety here. So hence, I'm going to rewrite the dilution equation here. EP for equation, just abbreviated. Note that conventionally it is M1V1, concentrated solution is equal to M2V2. Of course, M molarity, V is volume. Let's identify what we're looking for, first of all. So we're going to identify the unknown as we've done in previous problems, and then we'll identify the data that's given or our known. But the data that was given was, in fact, our unknown is volume 1 in milliliters is what we're looking for. So here is my unknown, the volume 1 in the concentrated solution. We were given, however, this is the information that was, in fact, given to us. Let's extend that, scroll that up a little more. Scroll it up a little more so we can have a little room to work. We were given the molarity of the concentrated solution, or stock solution, was 2.00 molar solution. Note we are looking for the V1. We were also given a molarity of the dilute solution, which happened to be 0.300 molar solution, and hence we were also given a volume of the dilute solution, which in this case was 0.50 liters. All right, we're good to go. We've identified the unknown, we've also identified the given, and we are at a point to where we can plug in the data and solve for our original volume 1 of the stock solution. Let's rewrite it. We've got M1V1, conventional way again of the dilution equation expression. Our molarity, number 1, was 2.00 molar solution. Again, this is a concentrated stock. V1, in fact, we don't know the V1. Now let's plug in the data for M2V2. M2, in fact, was 0.300 molar solution. And the volume, in fact, was times 0.50 liter. Now note, there are several ways that we could have done it. We could have first isolated our unknown, which was V1, and that expression would in fact be V1 is equal to molarity 2, volume 2 divided by M1, or, as I've done here, we can plug in the data and then rearrange, hence that we isolate the V1 and then solve for the quantitative value of V1. So let's do that. Well, I've got 2.00 molarity on this side. Let's divide both sides by that. So hence I have 2.00 molar solution. And hence our V1 comes out to a molar solution of approximately, the V1 comes out to a volume of approximately 0.075 liter. Now note, let's take a look at this. Here, this is of the stock. This is the stock solution. Now this number seems to make sense. And why does it make sense? Well, it makes sense because our original volume was in fact 0.50 liter. Our solved volume 1 was in fact 0.075 liter. Well, what took place here? Well, what took place here was in fact that the stock volume in fact decreased here. And that makes sense because on the other side, the molarity for the concentrated solution in fact was higher than the molarity of the dilute solution. In fact, the comparison would in fact have been to the stock was 2.00 molar solution as compared to 0.300 molar solution. So note that we in fact can, by inspection, identify that this solution here, in terms of our volume that we solved, in fact is correct. So let's move ahead. Let's do one other dilution problem. We're going to go to our second dilution problem. Let me scroll this. Here it is, right here. Again, let's take a look at this problem. Here's our second dilution equation problem, and it reads as such. If 0.50 liter of 5.00 molar stock solution of HCl is diluted to make 2.0 liter of solution, dilute solution, how much HCl in grams is in the solution? Okay, so we're looking for grams. Well, let's go ahead, let's go back to our smart board. Let's go back to the smart board. Okay, and let's identify our given. Again, this is a dilution equation problem, our second one. Let's rewrite the convention expression, which is M1V1 equals M2V2, all in uppercase. Let's identify our unknown, as we typically do in these types of problems. Our unknown for our second dilution problem, in fact, was to solve for the dilute molarity. Solve, so the M2 is our unknown. Well, let's identify now our given and all the data that was provided for us in the given. Well, what was provided for us was, first of all, our M1, or molarity 1, was equal to 5.00 molarity HCl, hydrochloric acid, or hydrogen chloride. Our volume 1, corresponding to that molarity, was in fact 0.50 liter. Our volume 2, which is of the dilute solution, was calculated at 2.0 liter, and we in fact are solving for M2. Let's scroll that up. We'll scroll that up just a little more. Okay, so let's rewrite this. M1V1 equals M2V2. Again, we're looking for the dilute solution, the molarity, and this is our unknown. So let's take this, let's rearrange it such that molarity of the dilute solution is expressed in terms of molarity, volume. So hence we have M2 equals M1V1 divided by V2. Okay, let's go ahead and plug in the data that we've been provided. M1, in fact, is 5.00 molar solution. We were also given its volume at times 0.50 liter. And then our volume 2 for the dilute solution was in fact 2.0 liters. 2.0 liters. Plug this information here into our calculator, and hence we should have a molarity of the dilute solution, which in fact comes to approximately 1.25 molar solution of the dilute solution. Note that this is, of course, lower than the other, but our volume is higher than that of the stock. So we've done a second dilution equation, and we are ready to move forward. And our next stop will be on molality. And it's, again, a solution concentration type problem. So let's go ahead and let's get back to our PowerPoint here. Well, let's first of all, now let's talk about molality. All right, molality, first of all, and then we'll do a couple of problems. So molality. Note that molality, in fact, is expressed as little m, kind of commonplace also with mass, little m, lowercase m, in terms typically in grams. Molality is equal to moles of solute divided by kilograms of solvent. So again, the relationship of molality in terms of solution concentration is moles of solute divided by kilograms of solvent. Okay? Well, let's look at our first problem. Let's go back and let's look at our first molality problem. Okay, we're almost there. All right, let's go ahead and read this. A researcher adds 4.5 grams of sodium chloride to 100 grams of water. Calculate the molality of the solution. Very straightforward problem, very quantitatively, very simple problem for us to solve. So let's go back to our smartboard, see if we can get back on that. Okay. Okay. Again, this is a molality problem that we're solving. Well, let's identify what our unknown is. Well, the unknown was conventional solving for the molality of the solution. So we are solving for little m of the solution. That's our unknown. Okay. Let's identify the given information that was provided for us in our problem as we read it. Given information, we were given 4.5 grams of sodium chloride. Note that our solute in this. And it was also provided for us was 100 grams of H2O. H2O. Now note that this is our solvent. And the expression of molality, in fact, is the relationship of moles to kilogram solvent. So let's go ahead and take this before we plug in any data in our equation. Let's change this and convert the grams to kilograms, which we can, of course, move the understood decimal point to 3 places to the left, and hence we have 0.1 kilogram of H2O, and that, in fact, is equal to our kilogram solvent. Kilogram solvent. Okay? So we've got that. Now know that we are looking for, our unknown is the mass of the solute. Mass of the solute. So let's go ahead and solve for our molar mass of sodium chloride, because we'll certainly need that in solving for the number of grams in the sodium chloride of our solvent. Well, note that the molar mass of sodium chloride, in fact, is approximately 58 grams per mole. 58 grams per mole. Okay, let's scroll that up. So we've got 58 grams per mole. Now, let me rewrite the conventional expression for the molality, which is little m is equal to moles solute per, or divided by, kilogram solvent. We are now in a position to plug in the data that was given to us, and in fact we will do so. So let's do the moles of solvent. That solvent, in fact, was at this point, was the sodium chloride. Now note that we were given 4.5 grams of sodium chloride. To get the moles, of course, we need to divide that by its molar mass, which was calculated at 59 grams per mole. Okay? And the kilogram of solvent, or 100 grams of water, which is a solvent, or converted to 0.1 kilogram solvent. Plug this data in, and so hence our molality. We plug this into our calculator, and our molality, or little m, in fact, should come to approximately 0.77 molal solution, or mole kilograms. Mole kilograms would be the unit. And that is our first expression and problem in molality. Well, let's do one more problem in molality. All right, let's go back to our problems here. Here's our second problem. Let's adjust this. Okay, here's our second problem in molality. How much barium hydroxide in grams is needed to make a 1.00 molal aqueous solution? So let's go back to our smartboard. Love those smartboards. Let's go back to our smartboard. Okay. All right, and here we go, we're at the smartboard now. Again, this is our second problem of molality. Let me rewrite molality and how it's conventionally written. Moles of solute per kilogram solvent. Per kilogram solvent. Okay? Well, let's look and see what we were given in terms of our unknown. Our unknown, this is what we're looking for in this problem. In the problem, it stated that we wanted to identify the mass in grams of the barium hydroxide. So mass in grams of the barium hydroxide. Okay? No doubt that is our solute. While we're here, we need to calculate the molar mass. So let's just go ahead and calculate the molar mass of barium hydroxide. Okay? And that equals approximately 171.3 grams per mole. Okay? Well, there was just one other piece of information that was provided for us. Let me extend that so we have a little room to work. We were also given a solution of molality, that is, of 1.00 molal solution. Okay? And we are looking for, in fact, the mass in grams of the barium hydroxide. Okay, well, we've got all the information that we need. Let's go ahead and plug it in the conventional expression for molality, which in fact is little m is equal to moles of solute divided by kilogram solvent. Okay, well, let's plug in we are looking for, in fact, the mass here. So let's put another expression on that. Let's rewrite this such that we have another expression for mole solute. So hence we have, let's scroll that up just a little more. So hence we have molal equals mass in grams of the barium hydroxide, really is what we're looking for. That's our unknown, divided by its molar mass, again, of the barium hydroxide, divided by the kilogram solvent. Now let's rearrange this such that we can isolate the mass of what we're looking for and express it in terms of molar mass, molal, kilogram solvent. Okay, so that's what we'll do. Let's rearrange this. That always seems to be an easier way to rearrange, plug data in, calculate. So let's rearrange this. So hence we have got mass is equal to molal solution times our kilogram in solvent times the molar mass of the solvent, which again is barium hydroxide, the molar mass of that. All right, so we've got this rearranged such that we can plug in our data and then we can calculate the mass in grams. So let's go ahead and do that. Well, the molal that was given to us was in fact 1.00 molal solution times kilograms, the kilogram solvent, in fact, was kilogram solvent per 1 kilogram solvent, so it would be 1 kilogram solvent, okay, times our molar mass of the barium hydroxide, which in this case is 171.3 grams per mole, and hence our solution for mass in grams, we should get a total of approximately, well, let's take a look at this. 1 times 1 times 171, pretty easy calculation there. So our mass in terms of grams for the barium hydroxide, in fact, is 171.3 grams. And again, this is of the barium hydroxide, and we have just solved our second molal or molality equation. All right, we've got one other item. One other item, and we'll finish this off. Let's go back to our PowerPoint. And our last problem that we're going to do is in fact called mole fraction. Again, another expression to identify solution concentration. Let's blow this up first of all. Okay. This is mole fraction. Now note, the problem reads as such. What is the mole fraction of sodium hydroxide in an aqueous solution that contains 22.8% of sodium hydroxide by mass. Okay, well, let's go back to our smartboard. Let's get back to our smartboard. Let's try that one more time. Back to our smartboard. Okay, here we go. Now let me talk a little bit about mole fraction. Mole fraction. Okay. Mole fraction, in fact, can be expressed in identifying the solute versus the total moles of the solvent and solvent, or the solvent versus the total moles of the solvent plus the solid. So our expression that is conventionally done, x of A, and this represents the solvent mole fraction, x of A, solvent mole fraction, and this in fact is equal to the moles of the solvent divided by the moles of the solvent plus the moles of the solute, and hence our expression for mole fraction when identifying what is the mole fraction for the solvent of our solution. Now let's go one step further. Now note we can also do the solute, and typically x of B, uppercase X, is the solute expression for the solute mole fraction. Now note this is very similar to the solvent, so it is expressed as the moles of solute, again divided by the total, which would be N of A plus N of B, or the total number of moles in that particular solution. Solvent, solute. Well, we've got a problem. Now let's identify what we have here. Our unknown is, in the problem that we originally identified, our unknown is, we are looking for the x of B of sodium hydroxide, x of B. Now note the x of B, by convention, this is the solute. I'm going to abbreviate this mole fraction. This is the solute mole fraction. Okay, let's identify, that's our unknown. We've got that. Let's extend this. Let's provide or write the information of the given.